So there's another theorem or another rule, call it what you will, and it's much like Chebyshev's theorem, but this one's called the empirical rule. And the empirical rule says your data has to look like this, and this is like a shape, which is important in statistics because it's called a bell-shaped distribution or the normal curve. And when data comes into this format, then there's a lot of research and work that's done about data that's in the bell-shaped distribution or in the normal curve distribution. So what this is showing us is, let's say we had data about like scores on a test for 10,000 students. Some students are going to do really poorly. They'll be down here. Some students will have aced it, done really great, or got really high scores. They'll be up here. Most people will be average. They'll be right in the middle. That's the definition of average. And there'll be like a ramp up to it and a ramp down from it, from average on both sides. That's a bell-shaped distribution. It's called the bell-shaped distribution because it kind of looks like a bell, right? So just to like put that image in your head, here's a bell, right? Kind of goes up and it comes back down, goes up, comes back down, right? Up, comes back down, up, comes back down. So it's called a bell-shaped distribution because it looks like a bell, and it's also called a normal curve. And so the empirical rule applies to data that's in this format. And I think a fair amount of data in the world falls into this format, right? Or it's just normal distribution. I don't know how much, but that's just my sense. Again, I didn't get my doctorate in statistics, but I've taken it 1, 2 times, and I've taught it this is my second time teaching it, so I'm starting to become more familiar with the basics of it. So the empirical rule applies to when your data is in this type of bell-shaped distribution, and when your data is in that distribution, then this is what applies. Approximately 68% of the data is within 1 standard deviation, 95% is within 2 standard deviations, and 99.7% of the data is within 3 standard deviations. So we could compare the 68, 95, 99, 1, 2, and 3 with Chebyshev's, and Chebyshev's was, what was it? Oh my gosh. So here we have 68, 95, 99. And we're just going to go with 95, 99 at 2 and 3. And at 2 we have 95 versus 89. Or at 2 we have 75 versus 75 at 2 versus 95 at 2. And we have 89 at 3 versus 99.7 at 3. So the empirical rule allows us to really have more insight and clarity on how much of the data is within, like the data is more closely grouped to the mean within a certain number of standard deviations when it follows this bell-shaped distribution. Okay, so that's the empirical rule. It's a lot like Chebyshev's theorem. There's no formula that we're going to use, but it does just say 1, 2, and 3. This much of the data is within these areas. And if you're doing assignments in statistics, sometimes you might be asked, like, hey, this data is normally distributed. It follows the bell-shaped curve, and the question is about like this first one we did where this was the mean, and here was between 60 and 80. How many of the students are between 60 and 80 if the data is normally distributed? You'd say, well, according to the empirical rule, that's 2 distributions, right? 60 to 80s within 2 standard deviations. That's why I want to say 2 standard deviations of the mean. So 95% of the students fall within 60 and 80 according to the empirical rule, right? If the data is normally distributed. So when data are believed to approximate a bell-shaped distribution, empirical rule can be used to determine the percentage of data values that must be within a specified number of standard deviations of the mean. The empirical rule is based on the normal distribution, which is covered in Chapter 6. All right, that's the empirical rule.